Welcome back to our factorial analysis of variance tutorial in SPSS. And last time we went through introduction with a little one-way analysis of variance and then went to a factorial model. I'm going to go back over that model. Under analysis of variance, we did a general linear model. We went to univariate, and we placed our dependent variable of labs into on the dependent variable, and our factors are both fixed, so group and time are in our fixed factors section of our dialog box here. Under options, we checked off a whole bunch of our displays that we'd like to see. I'm also this time going to go ahead, I want to see some of the group means in a little more detail. I'm going to go ahead and put display group means in here. If I wanted to, I could click compare main effects. I'm not going to do that for right now. Go ahead and click continue. Under save in our text, and we use this sometimes in examining some of the assumptions of our model, we could go ahead and save unstandardized residuals. So the raw residual, we'll go ahead and see that will be produced in our data set. So we want to save that from this model. I'll go ahead and click continue. We're going to go ahead and click OK. We get the same model we got before. Again, we went through and described the means before and the Levene's test. I won't do that this time. We talked a little bit about our model here. I'll go in a little bit more detail this time. So first, under group means, under group independent variable group, the difference in the means there across time, we saw that f value was significant. F of 21 is significant at the 0.05 level or lower. But just so you know, and I sort of went over this with the error term, our group effect, our mean square of 246 is divided by that error term, our within mean squares, our mean square for within, the difference we'd expect just based on being a person, right, in these types of groups is 11.53. So we take that 246 and divide it by 11.5, and we end up with that value of 21. And we went over this in class, but that's just a reminder. And then we see that that p-value there, that significant value, that p-value for the omnibus f test is significant. So this means that there's a difference. Well, there's a significant difference in the dependent variable here based on attractiveness. So we know that regardless of time of day, attractiveness has some importance on this value. So we want to see that there's no interaction term, because if there was a significant interaction, that could impact how we interpret this. But since there's not a significant interaction, that means that there's this unique effect. And in this case, we would say it's relatively independent, controlling for time of day. So time of day has been controlled for that effect using our type 3 sums of squares. So in our hypothesis testing language, we can say that we reject the null hypothesis, that in the population the means of attractiveness are equal. Doesn't mean we accept the alternative, but amongst the plausible alternatives, we accept the fact that there's a difference amongst the groups. And we can do the same thing for time. We can see time, we can see that that value is 712. That divided by 11.5 is 61. There's a very large f value, and that is significant at the 0.05 level or lower. And we could say the same thing here, that this indicates a significant effect on the dependent variable of attractiveness across all the groups. And that we can say that there's a unique effect, especially considering that the interaction term is not significant. When this interaction term is significant, it becomes more difficult to interpret, and we usually say that the interaction term takes precedence in interpretation first, and then we look to see if there's anything else to explain in the main effect. This time around, I asked for some of those means when I went to analyze, general linear model, and univariate. One of the things I asked for was display means for overall group time and group by time. I'm just going to cancel that out. Well, first thing I have here is our grand mean. Our gram mean is 18.406, and if we look up here, we see, if we look up before we ran with our descriptive statistics all the way down, 18.406 is right here. So we see our gram mean is 18.4. We can go through and we can say that this represents the overall mean no matter what group or time or anything. So it's the overall mean for the dependent variable, ignoring all of the differences between groups and times. Now we have overall differences within group collapsing over time. We saw that in the last video as well, and we can see that this is for a level of attractiveness 1, 2, 3, 4. We can see that the mean for each one of those, we see this increasing mean. For time, we see the difference, the mean of time collapsing over groups. 23 versus 13 seems pretty big to me, and we tested that effect, and that was significant. That means group 1 is significantly larger than group 2. So we don't even need that post hoc analysis just for time. And we go down to our post hoc tests. We looked at these before, and we see using our Tukey's test, we can go in by the cell level and say, is group 1 different than group 2? Is group 1 different than group 3? We can't really, we've already looked at differences between time effects. I'll just come back up here for those group differences. We see the cell level means, we saw those earlier, and we can see if we were to take group 1 and we look at the difference there, this group versus 15.25 and 7 looks like a relatively large effect there. We look within each one of these groups and we can see look like pretty big differences within group on time. That doesn't mean there's an interaction. That's just at the cell level we can see that there is a difference going on there. And we see that for our dependent variable of labs, looking across differences in groups, again, there's significance. I always think of this Tukey's HSD test as sort of the opposite. We're looking to see which of the subtests pulled together here. So 1 is separate. We're trying to see if 2 and 3 should be together, and 3 and 4 should be together. Next, we come down to the spread here versus the level of plots. We have our spread, our standard deviation, and our mean here. We can see that for the dependent variable, these standard deviations against, these are basically, if you take a look, 2, 3, 4, 5, 6, 7, 8, we have our cell means going on here. We have group by time. Maybe these will be helpful for us if we're starting to look at whether or not there was a violation of Levine's test. We might come here and start to look to see, hey, was there a linear effect? Should I do some sort of transformation that can help with that? So this could help us sort of pick through whether there's a solution to heterogeneity in our model, should it actually exist. So for example, if there's a linear relationship between the variance that we see here, the standard deviations and these means, then we could transform the data. Maybe you could take the square root of the dependent variable, but it's not always a perfect solution. So that's just one way of following up on our homogeneity test. And again, here we have our estimated marginal means, which we talked about in the last video. This time around, we also asked for our residuals. So we asked for the unstandardized residuals, and here they are. So we can go back, we can see that our lab score was 15. And when we go back to our data, we can see that for group 1, time 1, the mean overall was 15.250. And our residual is negative 0.25. That's the difference between lab minus that cell mean. So we get a residual, and we do that for each one of these variables. Well, SPSS did it for us, but we could easily do that ourselves. Now we're going to test one of the effects of normality. We did a little bit of normality in our last using just a one-way analysis of variance. But let's go ahead and check our test for normality here in SPSS. We're going to go ahead under Analyze, under Descriptives, we're going to select Explore. We will put in our residual into our model here. We're going to go ahead and plot a few things. Plots are very useful for us. Maybe we'll plot the stem and leaf and the histogram. Also, let's do a normality test because it's easy to do in SPSS. And it gives us a chance to look at what's going on. I'm going to go ahead and click OK. Just like last time, we get our descriptives. So last time we did this with a univariate model, and we can check to see whether skew and kurtosis are large. In this case, they're not above a plus or minus 2, so the absolute value is under 2. We have a 0.4 and a negative 0.16. Those are pretty good values of kurtosis and skew. So that's one indicator that we're have a normal distribution that we might be looking at. We can see that the test here, we see that it is not significant, so we like that as well. And then we can go look at our distribution. We see that it doesn't really look too bad as far as the normal distribution goes. So, the histogram is slightly positive, but we could also see that based on our skewness. So 0.4 is saying it was slightly positive, but not extraordinary positive, plus or minus 2. We have our stem and leaf, which I always think of as our, and here we have our histogram, and it's the same shape, relatively speaking. It's just on its side. You should have done stem and leaves in your previous class. Stem and leaf, we have the root of the value as the stem for our residual, and then the leaf is the decimal place, and we see that we sort of, I like this way because you get a little bit more information, but the histograms are good enough to look at for in this case. We also get our QQ plots. Everything's pretty much right there on the line. We have a little separation up here, which isn't surprising given our skew, but in general, this is very helpful when we see like large departures from the line of expected versus observed values here for these residuals. We start to suspect where the non-normality is in our model. And finally, I'll talk a little bit about our box plot. I like box plots. They help us look at the distribution from a plots from a graphical perspective with just less data. We see that the median here is right around 0. We see that most of the data lies within very close here, very close to this point of 0, and this helps us to see whether or not where the skew might be a little bit into the positive as we go in this direction. And not that it's significant, but you can just see that here. I kind of almost think about this like looking at a histogram from the top down, and it tells us also that there's not really any extreme outliers. SPSS would plot any outliers beyond these lines here, if there were any. We'll go ahead and stop there for now, and in our next video we'll extend out some of the interpretations and move into analysis of covariance, still using our fixed effects models.